Now let's look at some applications in biophysics especially, because, it's fun, it's bio, it's us humans and all. But let's see. The most famous muscle, or the one that people love to show off, is our biceps, the little lump there. Especially guys like to show this off for some reason. But think of it. Why can bones move in the first place? Why is there a lump there? What's happening? Truth is, all your bones are like the rods we looked at earlier. Okay, those straight line rods, just all over. Basically, your skeleton is just a bunch of straight sticks. But what makes you able to move are the muscles that are pulling the sticks. So oftentimes you have like pivots, and then you have muscles pulling up, muscles pulling backwards, things like that. So you see here, there's one joint where the muscle pulls the bone. Here's another joint. And all these are what causes a torque on your arms, okay? So your bones and muscles are actually working together so that you can move, so that you can do this, so they can do this. You can do, I don't know, all kinds of things, swing your arm around. It's all because of torque. That's why you can move lah. It's like rotating. I guess our necks are also rotating. Very complicated kind of torque, but move your muscles around, stretch a bit. Don't sit in front of the computer too long. Exert some torque using your muscles and bones. Okay, let's look at a past year question. First one, forearm torque. Ooh, look at that diagram on the right. A man holds a load stationary in his hand. The combined weight is 20. What is the vertical force needed in the biceps? Whoo, okay, first things to note. The load is held stationary. I repeat, the load is held stationary. Stationary meaning that your net torque is 0. Okay, so let me repeat that. Your net torque is 0, which also means clockwise torque equals to anti-clockwise torque, like what we talked about in the previous video. Okay, so all the clockwise torque balances out with the anti-clockwise torque, so nothing rotates. It's just stationary, holding the load there. So how can we calculate this? We need a vertical force. Okay, you see a diagram like this, don't panic. It's the same thing as what we looked at earlier. You have a rod. You have the weight of the arm plus the hand. So that's given to us as 20 newtons. Right there, 20 newton. So that's a force that's going to cause the hand to just, drop down because there's a weight. And then there's the big heavy load, the box, causing a clockwise torque because of its force of 100 newton. So there's also what the muscle will do, which is the one right here. Bicep muscle's gonna contract and pull up the whole bone to support that. And you can represent that with a simple arrow. And that's what I'm trying to find. What is this force needed? Now they didn't exactly tell us what the pivot point is, but remember we can choose, and it's usually a good idea to choose the hinge. So in this case the elbow is the hinge, so that's where your forearm will rotate about. So okay, let's do that. Let's choose the elbow as the hinge. Now we solve things like normal. Okay, so we're going to shortcut a bit. I'm just going to do clockwise torque equals anti-clockwise torque. So clockwise torque equals anti-clockwise torque. So what's going to push clockwise? First we have that the weight of your entire forearm. So that's 20 newton. You know what? Let me just make it color-coded. Why not? Since I have so many colors available. 20 newton times, how far is it away? Check and see. 10 cm. Cm. Let's change it to meters. So 0.1 meters. Okay, what else? What else? There's another one. The 100. So 100 newton from the load, the box that you're trying to carry. And how far is the entire forearm? 32 cm. So 0.32. That equals to anti-clockwise. We don't know what that is. Great. Okay, so we'll just say F times some distance, 4 cm only. Wow, very short. 0.04. Okay, so we plug in our calculator to see what we get for F. You can do ahead. Don't need to wait for me if you got it. Okay, so let me just plug it in a bit. 0.1, 100, 0.32 divided by, whoops, divided by 0.04. 850 newtons. 850 newtons. There we go. So this means the muscle, the poor muscle biceps, have to exert a force of 850 newtons, which is about, wow, if you change that to kg, that's about 85 kg. Okay, so 850 newtons by the bicep muscle. So you could say, what affects a person's strength? Well, it could be how much that muscle, the bicep muscle, can contract. That would be how much force it can exert. Or maybe the person's bicep muscle is attached much further out. Like maybe, you know, if I draw on the picture here, maybe the bicep muscle is attached a little further here. Like, you know, apes, if you see monkeys, their arms are actually not quite straight like this. They have like an extra muscle coming out. That make their hands much stronger. Or you could have shorter arms. So then your distance is much shorter between the pivot and your load. So that will enable you to exert much stronger torque if you're arm wrestling someone or climbing a tree or things like that. Okay? So whenever you see any kinds of body related, anatomy related questions, just remember it's all torques. Simplify it down to a rod like that one over there. Okay. Here's 2 questions that will help us think about how to use the different ways of finding torque that we talked about in the previous video. First one's about push-ups. Okay, so look around. You see 1, 2, and 3. They're all trying to do push-up, but what's different is that they're doing it at a different height. So the first person is doing it on the floor. Second person is doing it on the bench. And the last person is just doing it against the wall. Now, to be honest, I cannot do the first push-up. Somehow, I can go down, but I cannot go up already. Anyway, let's see. How do we think of this in terms of torques and bars? You gotta model the human body as a bar. Okay, so imagine that the entire human body is one bar. Just draw very lightly. What's the thing that's making it hard to do push-ups? What's pulling it down? Weight, human weight. Okay, so I'm going to draw an arrow to represent weight. For ladies, the center of gravity is somewhere at the hips, so I'm going to draw a, let's use blue color. Center of, weight, there we go. W, or mg. I'll use mg. Mg is nicer. So it's a weight pulling down, and what other forces are acting just for fun? Let's draw them out. Good practice, okay? So, the hand will experience a reaction force from the floor, okay, both hands actually. So, got a reaction force there, for the other arm also one. Got another reaction force at the foot. Holding up. And actually, this person's wearing shoes, so there's a small friction force this way to prevent the legs from sliding back. Okay, if you're trying to do this push-up position on a slippery floor, it's very hard because your legs just keep slipping out. So it's good to wear good shoes when you're working out at the gym or at home. But I think this is all the arrows we need to draw. Okay, one more thing. There's an angle of push-up. Just going to squeeze it in there, theta, which is between the legs and the floor. Then you have the same in the second picture. Some weight of the body, mg. Reaction forces are acting on the hands by the floor because the hands are pushing the floor. Also at the legs, and some bit of friction to prevent the legs from just sliding back. And the angle, of course. Last one, wow, this thing is completely different now, the person standing up. So you have some bit of reaction. Some bit of reaction here. Friction is probably just almost zero, but just a little bit. Friction, R. and a huge angle now. This whole thing is theta. And weight. Oh my goodness, forgot weight. Weight. mg. Okay, so that's how we draw free body diagrams, literally on the body. And the question is, I repeat, which one is the easiest to do? By experience, you will know the answer. Go and try it out. If you're sitting there too long, get your body working. You know which one is easier by experience, but we're going to look at the math, how to make sense of your experience. Okay, let's look back at the first picture. If we redraw it as a triangle, it will help us see better what's the forces at play, but we need to choose a pivot point. Shall I choose the elbow? I could choose the elbow, but there's a lot of friction and other stuff there which I don't want to bother about. So I'm gonna look at the foot as the pivot point. There, I drew a little dot. Pivot. Okay. Then now we can draw out the other parts. Okay. So we have the weight. Some weight somewhere near the middle. Oh, W, mg. This is mg. Then you have your angle, theta. We need something for the length of the body. Let's say the person's whole length is L. So halfway to the weight is L over 2 to this point. Okay. So then your arm will need to do a R, force R to push up somewhere here. Okay. How much to push up or push down on the floor so that the floor pushes up. And then there's the head up there, which we don't care. We just want to look at the middle part. So we have mg, and we want to find out how much torque is the weight causing in the first place, so that we can think of what reaction to do in order to push up. So how much is the weight causing? We got a little problem because your mg is not exactly perpendicular to the body. So for this case, I'm going to choose to resolve the weight, make the weight perpendicular by doing this. So I draw a perpendicular line because I want to find what is this perpendicular weight. So this weight is going to be, what's the angle? If theta is that one, theta is also this one. By trigonometry, okay, you can try it out. Solving all your angles. So that one will be adjacent hypotenuse, ka. So cos theta. mg, oh no, no space. Give me a second to rewrite this. mg cos theta. That is the amount of weight that will cause a torque clockwise. Okay, the weight of your body is going to pull the body down because weight and torque. Okay, so how much force do we actually need? Let's write it out. So this will cause a clockwise torque, the weight of, let's use perpendicular force times distance. So we already found our perpendicular force, which is the perpendicular weight. Okay, this fella gonna cause a force. That will be mg cos theta. And roughly, how far is this weight from the pivot point? We estimated it's roughly L over 2. It's a good estimate for most people. Some people are anomalies. They have very long legs or very short bodies, or very long bodies, very short legs. Anyway, so we got clockwise torque, which is L over 2 mg cos theta. And that's it. That's how much torque you need to counter if you want to push your body up. So as you see from picture to picture, what is changing? Theta is actually increasing. Okay, so as you go from picture to picture, your theta is increasing because you're at a higher and higher angle until eventually you're against the wall. Okay, so theta increasing. So what happens to the cosine? I'm going to recap a bit. As you go from the left to the right picture, your cosine of theta is... Side note. There's a maths thing called the cosine graph. Cosine graphs generally look like this. Boo. And anyway, I can keep going and like that. But you have an angle. This is 180, 90 degrees. So as your angle gets bigger and bigger, your cosine gets smaller and smaller. See the graph going down? This is cosine of theta. Okay, so as angle increase, cosine theta decreases. And if you look back at the equation, this cosine theta is getting smaller, which means everything else is fixed, right? mg is fixed, L is fixed. Means your torque is also getting smaller. Therefore, you can say your torque also decreases. Or I should say clockwise torque decreases. Okay, so as you move from a lower to a higher push-up, it's your weight of your body is causing a smaller torque because of the angle, just because of the angle of it. So it's much easier to use your arms to get a counter torque in order to do your push-ups. Okay, so go through again carefully, see how you can use the math to support your experience and make sense of it. Because the next one will be quite interesting, maybe a little bit more tricky too. In this picture, the person's carrying a barbell and doing squats. FYI, the barbell looks something like this. You know those things in gym where they carry it and then they do their squats. Sometimes the very strong people, they'll put many stacked together and then they do this. Okay, that's a barbell. Barbell, I think I spelled it correctly. You know, dumbbell, barbell. Okay, barbell. Anyway, we're going to do the same thing to the human body. We'll model it as a rod. Actually, there's many rods here, but for simplicity's sake, okay, reduce headache a bit, we're going to say, look at the abdomen part. So the pivot in this case would be the hip bone, then a rod of some length. You know, I'll just call it D. D. It's my D. D. From the hip to the place where the person is holding the barbell. Okay, so the barbell will have a tremendous weight, very heavy, sometimes 100 kg, 200 kg, especially those who are really like weightlifters. We'll just say this is mg. For this case, I'm not going to bother about the human body weight because just assume it's part of this mg inside here because it's so heavy and it'll make things complicated. Anyway, so that's that. There's an angle also from the floor to this rod, and an angle which is the same. The person's knee look kind of straight everywhere, so it's also the same angle, theta and theta. Then the person does another kind of squat, but now the barbell is behind on the shoulders, so something like that. Angle is a little bit smaller, still quite big. There's the same old weight from the barbell, mg, pulling it down. Oh, and I forgot the hip bone. Same thing, we have some D, whatever D it is, okay, different D. And the last one, the person just pushes the barbell down lower to the lower back and does lower back squat. Really hard to do, to stand up and do that. Same thing, we got a pivot at the hip, weight pulling down, mg. And of course the angle, which looks a bit smaller. Maybe this angle is something like, well, the first one could be 60 degrees, maybe 59, then 57. I don't know. It's roughly in that area, okay? Everyone's angle is different. You go try it out. Okay, so the question is, which one is hardest to do? You may know the answer if you have done all these kinds of exercises before. But if not, then we have to think of the maths reasoning behind it. So I'm going to draw a triangle, or try to draw a triangle. So that's the body length, D, at some angle, at the pivot. Then we have a force, the weight, pulling down. This is mg. Let me go extend that all the way and form a nice triangle for you. Okay, so now, we got a problem again. The force is not perpendicular to the rod. So how? Just now we changed, what did we do just now? We made the force perpendicular, so we use a component of weight. But in this case, let's do something different. Let's use the perpendicular distance instead. So distance perpendicular to the force will be this D perpendicular right here. So from the pivot to the force, okay, D perpendicular. So D perpendicular will be what again? Cosine, sine, tangent, check and see. Adjacent, hypotenuse, cosine. So D perpendicular is D cos theta. That's how you find the perpendicular distance. So let's calculate what's the torque generated by this barbell on this person's shoulders or arms. So the torque in this case will be force times perpendicular distance. Little bit different, don't forget. So force is just mg, good old mg, times perpendicular distance we already found was d cos theta. Okay, so as we look throughout the whole picture, what is changing? You see, as we move from left picture to right picture, the angle is getting smaller. So theta is decreasing. Which means, what is increasing or decreasing? How is cosine of theta changing? Cosine of theta is, okay, if you forget, draw the little cosine graph here again. It kind of looks like that. Okay, now you're decreasing, so you're going this way to a smaller angle. Means your cosine is getting bigger and bigger, closer to the value 1. So cosine theta is increasing in this case. Increasing. If you don't believe me, grab a calculator, plug in the small angle into cosine, and see what you get. Okay, so cosine theta is increasing, so this is getting bigger. How to draw bigger? Bigger. So if that's getting bigger, means the torque is getting bigger. But let's pause, let's check one more thing. Okay, so cosine theta increasing means as you go from picture left to picture right, d perpendicular, which is d cosine theta, is also increasing. Therefore, then you can say the last line, therefore your torque clockwise is increasing. So increase, increase, increase. Which means it's harder to do the one on the right, the one where you have to really pull that barbell down to your lower back. So if you want the, well, not the biggest muscles, if you want the hardest training, get a weight, put it on your lower back as low as you can, keep your knees straight, and then you do your squats. Plenty of time to do it at home when you have time, okay? Whew, so this is how you can think about biomechanics of the person's body, different ways of modeling the person as a rod. Okay, just like what we do, a rod, forces pulling here, forces pulling there, how you can think of it.